Chapter 8, Section 3, Day 1, Estimating a Population Mean. Learning targets for this lesson are to construct and interpret a confidence interval for a population mean, determine the sample size needed for a population mean with a specified margin of error, to describe how the margin of error of a confidence interval changes with the sample size and confidence level C, and determine sample statistics from a confidence interval. In the mystery mean activity that we did in Section 8.1, we've actually already calculated one of these. If you can remember back, what we did is we took the formula estimate plus or minus critical value times standard deviation of the statistic and evaluated the mystery mean to be between 230.99 and 250.59. Therefore, when we did this, the formula for calculating a confidence interval, when you knew what sigma was x bar plus or minus z star times sigma divided by the square root of n. The problem with this formula is we rarely know what the population standard deviation is. But before we worry about how to change this formula, let's talk about choosing a sample size first. If we need to choose a sample size for a study of means, our margin of error is z star times sigma divided by the square root of n. To get the number needed from the margin of error, we need to get a reasonable value for the population standard deviation from an earlier or pilot study, find the z critical value from the normal distribution, and set the expression for margin of error to be less than or equal to the margin of error that we're looking for, and solve. So here's an example. A researcher would like to estimate the mean cholesterol level of a particular variety of monkey that is often used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mu at the 95% confidence level. A previous study involving this variety of monkeys suggests the standard deviation of cholesterol level is about 5 milligrams per deciliter. The critical value for a 95% confidence level is 1.96. We're going to use sigma as 5, as suggested in the previous study, and we're going to use a margin error of 1 and set up this inequality. To solve this, we're going to multiply both sides of the equation by the square root of n. To get rid of the square root, we're going to square both sides. And to simplify, squaring that out on the calculator gives us 96.04. Remember, we always round these numbers up, so we're going to actually use 97 monkeys to ensure the margin of error is no more than 1 milligram per deciliter with 95% confidence. Now going back and calculating a confidence interval for means, we rarely again know sigma. So when the sampling distribution of x bar is close to normal, remember that we can find probabilities involving x bar by standardizing using our familiar formula. But again, we rarely know what sigma is. So what we do is replace sigma with a sample standard deviation denoted s sub x. So our equation becomes x bar minus mu divided by sigma, or s sub x divided by the square root of n. This no longer is our z distribution. It is not normal. It is a new statistic. When standardizing using s sub x instead of our sigma, we use a t distribution. A t distribution is going to have a different shape than a standard normal curve. It's still symmetric and has a single peak at 0, like a standard normal curve would. However, there's going to be much more area in the tails. Here's an example of a t statistic versus a z statistic, and you can notice this. Like any standardized statistic, t is going to tell us how far x bar, or sample average, is away from mu, or population mean, in standardized units. However, there is a different t distribution for each sample size taken, specified by its degrees of freedom. Degrees of freedom for a t distribution is n minus 1, and it's denoted t sub n minus 1. When standardizing, t is equal to x bar minus mu divided by sigma sub x over the square root of n, with n minus 1 being the degrees of freedom. There are several facts that are apparent when comparing a t-distribution to a standard normal distribution. Here in the picture you can see the purple curve is a standard normal curve, the red dashed line is a t-distribution with degrees of freedom of 2, and the light blue solid line is a t-distribution with 9 degrees of freedom. Some of those similarities and differences are: a t-distribution has a similar shape to a normal distribution. T is more spread out than a normal distribution. T has more probability in the tails, meaning that larger area under the tails. And if you compare the two t-distributions there, as the degrees of freedom increase, the t-distribution becomes more and more like a standard normal distribution. We can use Table B in the back of the book to determine what are called critical values, T star, for the t-distribution with different degrees of freedom. Let's look at an example. Suppose you want to find and construct a 95% confidence interval for the mean mu of a normal population based on a simple random sample of size 12. And I want to find the t critical value. Here's a portion of Table B that's in the back of the book. With 12 being the number in my sample, my degrees of freedom would be 11. I can go to the bottom of the table and find 95% confidence. The intersection of this column and row then, 2.201, will become my desired critical t star value. Our standard deviation of a sample statistic, or standard error of sample means, is given by s sub x divided by the square root of n, provided the conditions are met. So now when I want to construct a confidence interval for mu, I'm going to use the critical value t star instead of z star, with n minus 1 as my degrees of freedom. And my formula becomes x bar plus or minus t star times s sub x divided by the square root of n. These confidence intervals are calculated in a similar way to confidence intervals using proportions. And again, there must be 3 conditions met to be able to proceed. The conditions are, first off, it must be random. You must take a simple random sample. 2, your population distribution has to be normal, or the sample size must be large. Remember from central limit theorem, our sampling distribution will be normal no matter what the original distribution is, as long as n is greater than or equal to 30. And the independence condition, the 10% condition, must also be satisfied. Here again are the formula and conditions for calculating a one sample t interval for means when sigma is unknown. So let's look at an example. If you have your book, pause the video and read example on page 508. To construct a confidence interval, remember again the acronym PANIC. P stands for parameter. The parameter is the mean tension of all video terminals produced this day. A stands for assumptions and conditions. Checking the conditions, randomness, you're told that the 20 data screens come from a simple random sample. Normal. There is a problem here. Since the sample size is small, it's 20, which is not greater than 30, we must check to see if it's reasonable to believe the population distribution is normal. So we need to examine the distribution of sample data. To do this, we would take our sample data, type it into our calculator, and create a graph. I can either look at a dot plot, a box plot, or a normal quartile plot. I don't need to look at all three. One would suffice. In looking at any one of these three, there's no reason to doubt the normality of the population. None of these graphs show outliers, extreme outliers, or any skewness. The third condition is independence. Because we are sampling without replacement, we must check the 10% condition. We must assume that at least 200 video terminals are going to be produced that day. N is the name of the test. What we are running is a one sample t interval for means, or you could use the formula x bar plus or minus t star times s sub x divided by the square root of n. From our samples, we end up with an x bar of 306.32 millivolts, and our standard deviation is 36.21 millivolts. Next, I in panic stands for calculate the interval. Since we have 20 as our sample size, our degrees of freedom is 19, and with us collecting a 90% confidence interval, my t critical value should be 1.729. Along with the other values that have been given, and substituting them into the formula gives me this. Running that through my calculator gets me an interval of 292.32 to 320.32. The C in panic stands for conclusion and context. We are 90% confident that the true mean tension in the entire batch of video terminals produced that day is between 292.32 and 320.32 millivolts.